Oh, no, I can't. All right, that's different from yesterday. That's funny. Okay. Hang it, where did it go? Okay, there we go. All right. We have Thorsten. Thorsten is going to tell us, Thorsten is going to answer the question for us of what is equality.
Okay. Fine. Thank you. First of all, thank you for inviting me. I'm very happy to be here and meet people I'm not seeing so frequently. But yeah, my mic's on. Yeah. Can we adjust can we adjust this? Maybe. Hello. It's better. Better. Yeah. Okay. Good. Yeah. So I'm quite impressed about the quality of presentations here. Many of them are quite technical, which is good. Yeah, and some are really impressive presentations given by students. I mean, wow, cool. So what I wanted to do is wanted to discuss a bit more the ideas behind some design decisions. So it's a bit ambitious title, I admit this. And I should also remark that none of my colleagues who are joining work with are responsible for what I'm saying. Yeah. And so in the first part of the talk, I wanted to
No.
Oh yeah. I wanted to dispel some myth, and that so when I wrote this, I thought, oh, am I just preaching to the converted? But after being here for a few days, I realized that I'm in danger of being very controversial. And maybe can be. I mean, the talks here are very one directional. I'm quite happy if we suspend this. So heckling is permitted. Yeah. Don't break to the end if you feel you have to say something. Okay, so I want to dispel some myth about equality. I will just talk about equality. And okay, yeah, this is a quote by Conor McBride. It's paraphrasing. He remarked that in politics and type theory, equality is a deeply contentious issue. And I find one shouldn't leave. I like to talk about politics and I like to talk about equality and so on. I think, and also religion. That's another topic we want to cover. So I'm not. I meant as long as you're civil, right? I mean that's the point. You respect each other and you don't expect a conclusion. I mean you learn something by disagreeing. It's not always like happy ending ever after. Okay. So let me start with my myth. The first myth is that equality in type theory is something else. So maybe I should say this seems to be a bit formalist to me. I mean, obviously, people who work on type theory they think about it as a formal system, and it's something they do something with. But for me, I mean, where the formal systems come from, we have a sort of pre-mathematical, intuitive idea about we talk about equality. And when we design a formal system, and okay, I should add something else. I'm thinking here about type theory as a foundational system. I mean, I'm well aware it has lots of other features. Like, I mean, there's the synthetic use of the language of type theory, the model homotopy theory, which is very impressive and very important. And so the language of type theory in itself is interesting. But what I want to highlight is type theory as an expression of how I think, what I want to say, and basically trying to reflect, trying to make precise the reasoning, sort of intuitive reasoning in a formal system. So I think equality in type theory, there's people come up with all sorts of names for equality, like identifications or path type inspired by the sort of synthetic view. And I would say let's just call it equality. I mean, so what I'm saying here that in my view, the intuitive idea of equality should lead directly to the equality type. And yes, it's a type, but this should not surprise us, because when we are thinking of propositions at times, right? I think of it at least. So that we explain the notion of a proposition by the inhabitants of a type, and that's quite beautiful, because obviously otherwise we have to define what's proposition, and we have to define types. But this reduction of proposition to types is quite powerful, and it's also powerful in the sense that we are not limited to the kind of propositions we are used to, namely propositions which hide inhabitants. And hence, equality, as we know, is not a proposition but a type, and equality of structures is a structure. So this makes it different from traditional notions of equality, like in predicate logic. But but it doesn't mean it's anything else but equality. It's just my understanding of equality.
Since you want heckling, I mean, do you Martin looks at identity types and versus like observational equality types as equally intuitive?
Yes, so I will let's do the later bit, but thank you very much. So I would say that there is actually a very constrained choice of what an equality type can be. There's some criteria, and this rules out some of these choices. But that's actually one of my later bits. So I'll come back to that. Okay, any other hackers? Yeah? What about? Yeah. Yeah, okay, that also comes maybe out in the next slide, hopefully. Thank you very much. So yeah, this is this other myth, right? Maybe related to what you said, right? That the type theory has two equalities, definitional versus propositional. I hear this a lot, and that's from an argument. I say, our type theory is really weird. They have two equalities. Are these two equalities equal or what? But I would say no. There's only one. Only the equality type. In type theory, I can only, if I mean equality, I can only use equality type. I cannot talk about definitional equality. Not something available to me in type theory. Now, obviously, we do talk about definitional equality when we talk about type theory. So it's a difference talking in type theory, talking about type theory. And when you give a mathematical presentation, you often switch the levels. I mean, this is not just in type theory, this is in tradition. You talk in mathematics, but then you talk about mathematics. The nice proof is not a mathematical statement, right? It's something about this proof proceeds by blah blah blah. Is about the logic. Yeah.
Is it talking about type theory to like write down REFL as a proof of an equation?
No, it's a construction in type theory, right? Yeah, it's not talking. We're not talking about it. We give a. I mean, it's a bit like this: when you define a function, you know the code of the function, right? But by a function, we mean the mathematical object given by this code, and not the actual expression. Even so, to write down a function, you have to write down the code. So now a proof, an element of a type, or of a type which we view as a statement, we have to write it down somehow. We have to write method, but it's not something we talk about in the mathematics unless you do meta mathematics. That's what I mean.
I think the sense in which people think type theory has two equalities is that I have to know whether I can write REFL doing my.
Yes, so type theory is different, like from predicate logic, in that the system itself, the setup of the system, involves something we call equality, definitional equality. But yeah, but that's not the equality in the system. Okay, thank you. So here is the next myth. Equality is defined inductively by a level. I didn't bother to write down the ACTA code for this. So this is in my view, that's not a definition of equality. It reflects whatever equality you have. I mean, it it's not defining, I mean, it's defined, yeah, in what is called intentional type theory, which is also a bit of a weird place, I always think, because, for example, these type theories we're designing now, homotropic type theory or higher observational type theory, I would not call them intentional by any means. Actually, they are very extensional. They're more extensional than what is called extensional type theory. So I'm not sure I agree with this terminology, but in what I call intentional type theory, you have no definition of equality. You just define equality as identity. So that's this definition, which is not a definition that reflects the non-existing equality, which means that it actually works for inductive types, because equality for natural numbers is just identity, but it doesn't work for anything else. Right? Equality of function should not be identity of functions. I mean, having the same definition, because we cannot actually look into the definition. So all what I can see about a function is how it behaves, and hence two functions which behave the same way are indistinguishable and hence should be identified. So intentional type theory is really wrong, because it introduces something like a function type, but it doesn't introduce the corresponding equality. So it's really misleading. And the same is true for extremes or the universe of types, where we have different equalities. So to me, this is a very, very basic idea here. I guess maybe hopefully completely unsurprising. What is a type? So maybe in the past we thought of a type is given by some element, but actually I think that it's clear that a type is really given by its element and by its equality type, which then forces us to have an infinite power of equalities. And yeah, you know, this is the weak omega group, but leaving alone the particular mathematical concept, a type is given by its element and by its equality. The equality is not, so what I want to say is equality is not something external, like yet another type former. Yeah, we have pi types, sigma types, and equality types. I think that's misleading. We have certain type formers, and for every type former, to explain what the type former actually means, we have to say what the equality means. Okay. Sorry?
We do it. If you're in next W types, then probably the element is there.
Yeah, it's another index W type. No, the equality type of W types is another W type.
Yeah, the document, I mean, equality is itself a different type, so it doesn't need to be separately.
Sure, but I mean, what I'm saying is,
He's going to say.
You're the translator. You're the translator. Thank you. So yeah, I mean, if you introduce a W type, then what's the equality between the elements of the W type?
I think what he said, he was saying the identity type is an index W type.
Yeah.
But that's what he's saying.
That's what I'm saying.
Well, I'm saying that there are index W types, and one of them is what we traditionally call the identity type.
Yeah, I mean, or what I was saying is that
It's not wrong to have that thing.
no. What I'm saying is that identity type is not something so separate, which you once and forever define, but identity type is assigned for every type. And as you say, for an index W type, the identity type is yet another index W type. That's fine. You know, I'm actually that's the way we view it, right?
Well, but that's level 0. Applying for the index W type for your higher power.
Yes.
If you say like,
Yes, that's indeed what we're doing. Yeah. Okay. I'm not sure, but
Okay.
yeah, I mean, for example, equality of types is given by equivalence, which obviously is something we can also define beforehand. I mean, that's the point, that equality can be defined, could be defined as another type. In the sense of it. Okay.
I can help tackle you too.
Ah.
Are you claiming that the equality for different type, constructed types based on the structure of the type may be different depending on how the type is structured? But is it determined? Is it determined by the type? Are there different options? Is it an extra pre-parameter, like in the definition of a category where you can find the morphisms maybe in different ways? It's not determined by the structure.
I mean,
Or are you saying it is determined?
okay, but what I'm saying is to give a type, it's not enough to tell me what the elements are.
Yes.
You also have to give me the equality.
And how much freedom do I have in
I mean-
determining?
Okay, so what are the rules of equality, right? I mean, that's a good question, and I'm not asking, but there are obviously some conditions.
Different possibilities.
Yeah, I mean, I will get to this. Yeah, I mean, what determines equality abstractly?
Yeah.
In the moment, I'm just saying, to give a type, you give a type and an equality type. What's the constraints of the equality type? I'm not saying this is something we have
It's a little bit like saying to give a category, you say what the objects are and what the morphisms are.
Exactly. Yeah, exactly.
I'm on board.
Okay, so here I think we touched about this earlier. There is this idea of like there's sort of like some choices you can make. Equality could be this, and equality could be that. And I don't think so. I mean, I'm not going to claim that there is a unique way to define equality, but I don't think there's such a freedom. So I would say that the design space of what equality can be is highly constrained. And I think I already alleged to it earlier, what I call the Leibniz principle. I mean, let's look at intentional type theory. In intentional type theory, you have functions, and you cannot observe the definition of a function. Then two functions which are extensionally equal, what are they? I mean, they're not equal and they cannot distinguish them. I would think I understand a mathematical object as something which I construct in my mind. So all what I can do with it is do other constructions with it. And it's given by nothing else than what I can do with it. So two mathematical objects, like two functions, which behave the same way in another application, are indistinguishable and hence should be equal. Now you can argue, but you can never achieve the sort of completeness in the sense. But I would say this incompleteness which we have, for example, in intentional type theory, is really a structural incompleteness, not to do with proof theoretic strength. I mean, it doesn't matter how strong your system is, you will still not be able to prove functions equal. So to satisfy or at least approximate this Leibniz principle, we are forced, and I think we don't have a choice, then to accept function extensionality in univalence, because I mean, if you have two types which are isomorphic, you cannot distinguish them. That's the point. I mean, this is really something we get from type theory, because type theory it doesn't allow us to talk about elements of a type in isolation, like the set theory. So we can only talk about elements of type given associated to a type, and hence we cannot actually distinguish isomorphic structures. Since we cannot distinguish isomorphic structures, we don't have a choice but identifying them, saying they're equal, but I cannot see this. And hence we are also forced to accept that equality is not a proposition in the sense, but actually a type. So I think I'm arguing there isn't really a choice here. This is forced upon us. Okay, sorry. Any heckling on this? This one we already had a little discussion about this. So univalence is an axiom, and it's called univalence axiom. I always call it the univalence principle, because I think axioms shouldn't be used in type theory. Now I'm a bit careful. I mean, shouldn't be used. I'm not going to outlaw it. I'm not going to prohibit it. As I'm not outlawing the use of excluded method or axiom of choice. It's all cool, yeah, as long as you feel guilty about it. I mean, yeah, I mean, we use axioms in my mind. I mean, like look at Buchot as a stopgap, right? And that's okay. And maybe sometimes we don't know how to compute with a principle, and we have to learn this. But we know we want to have it. That's fair enough. The axioms as stopgaps, okay. So I find that axioms, in the sense of predicate logic, shouldn't be used in type theory because they interfere with computation. Yeah, I mean, they destroy the computational character of type theory. And to me, type theory, I mean, I want to be able to always compute something. If you give me something which should be a natural number, I want, at least in principle, be able to it should correspond, should be able to compute. Now, so I think good extensions of type theory, and we have seen a number of them, are actually some which preserve canonicity. So for me, a type theory is really a system which, as one of the properties, has this notion of canonicity. If I compute, I get really a canonical. And again, I'm not saying it should be illegal to use systems which are not canonical. Obviously, sometimes it's quite convenient, and sometimes you make more progress by making compromises. I'm not what to enforce this. Okay, so I used most of the time. Here's a summary of what I was saying. Let me say a few words about the design we are looking at. This higher observational type theory, and Mike is going to say more about this. So I wanted this. So to me, this approach is an attempt to implement, to realize the goals which I explained before. And you could say that a system like these cubical type theories, what I know best as cubical acta, are also along these lines. But I would say that something like cubical type theory is a reflection of this model construction, of the cubical model, which was important progress, because when we started to design homotopy type theory and wrote this book in Princeton, we didn't yet know how to compute with univalence. So we had this stopgap, I would say, univalence axiom. And then there was important progress. I mean, a number of people tried to overcome, I mean, to be able to compute this. And obviously, the Gothenburg team, Thierry and sorry, I mean, just think of Thierry first. They're able to give a constructive model, and then by reflecting this model into the syntax to give a type theory which has lots of nice properties. But I think I would like to have something more conceptual, something which is other in a way model independent, still justified by semantics, but the semantics shouldn't be so directly visible. And I think to my mind, this is what we try to achieve. So the key idea is equality is a logical relation. So what's the logical relation? For each type, we define a proof relevant relation, which is called a bridge. And importantly, every function preserves its relation. And this is called internal parametricity, and it's really been investigated a while ago by Bernardi, Moulin, and Kokong, I'm not giving all the names, who actually, so the idea is that this idea of parametricity, which is quite old with respect to Reynolds, it was usually implemented by separate calculus of relation. But once you have dependent types, you can identify the language you're using and the language you define the relations in. And this was the main idea by Jean-Philippe, how to do this. And moreover, this principle that every function is a congruence, which we call applied path, this principle can be implemented now as a constant or as a function in types theory. And Jean-Philippe discovered actually he had this problem that he didn't know how to define how to prove canonicity. The computations got stuck. And he then suggested this cubical interpretation with symmetries to overcome this problem. And we have recently revisited and fixed some issues, proved stuff in this Popper paper, which in a way is also input to MURI. So the semantics is a few category with permutation. So we still use cubes in the semantics, and more equality. Equality now I shouldn't say equality because these bridges and it supports logical. It exactly supports this internal parametricity. But as we know, this is not enough. This is not equality. And there are two ways to see this. So in the universe, when what is the bridge between two types? Bridge between two types is a relation. But obviously we wouldn't say that any two types between we have a relation should be equal, but clearly not equality. And that's why it's interesting that in this approach, like types like natural number and MURI actually are there the bridge is equality, but the one type where the bridges are not equality is exactly the universe, because the universe in a parametricity theory has this property that a relation is a bridge between types in the universe. And but correspondingly, what we don't have is transport. So the point is to fix both of these issues, and I think I now managed to run out of time.
Schedule is flexible.
You started a few minutes late.
Okay, so I would like to explain and give a quick explanation of what I mean, what this means. So how do we define a fibrant universe? First of all, there is an observation, or I think it's an exercise in the workbook, that we can define equivalent via relations. If we have two types, let's say A0, A1, and that's a type, and we have a relation, and let's call it A2. How can we say that this is an equivalent, that A0 and A1 are equivalent using this relation? And can you read this? Okay, Bob comes. Yeah, so how can we say that this is an equivalent? And actually, the idea is basically the same as the notion of a bijection in logic, in proposition, but we say that this is a graph of a function in both directions. Right? So how do I say this? Like I say fun in this direction for any A0 and A0 is contractible. So there exists the unique in A1 in A1. Okay, there's a sigma. Such that A2, A0, A1. Right? I mean, so this is quite a nice little observation that this type on its own, if I just have these two, this is equivalent to having a function from A0 to A1. Right? So this is one of the cool things in type theory that we can define, that we can recover functions as or via relations which has this property. And okay, because we are proof relevant, we say not that there exists unique A1, but there exists unique A1, unique proves that it's related, right? And but the point is, I can now say that the same relation is a function in the other direction. And use it. So given this definition of an equivalence, we can take it a bit apart. So what does this actually mean? If we get rid of contractible and the sigma type, it's really, so I use different names than in Maria. So I say that's a coercion from A0 to A1. Yeah, this is just the first component of this big sigma type. Then there is a proof that this holds. So for any A0 in A0, I have A2, A0, QA, A0. Okay? And I need the uniqueness, which I'm not going to spell out. He says for any A0 in A0, any pair A1 versus property is equal to what I've said here. Now, this uniqueness is a bit annoying, and also what I want to do is I want to define a universe of fibrant types. So really, what we want to do, we want to have a property that a type is fibrant and supports transport. So we want to introduce a predicate isfib, which given an element of U gives a proof that this is fibrant. So we want to identify, so we want to define a universe of fibrant types, which is a sigma type of a type A that is fibrant of A. Now I'm running on a visible blackboard everywhere. And how do we do this? I mean, at the microsurf, we can define it as a higher co-inductive type. So we are used to higher inductive types. And for higher inductive types, we say, okay, we define a type by saying, what are the elements, what are the equalities, what are the equalities of equalities, and so on. A higher co-inductive type is just the dual. We define the type by its projections, by saying, if we have an element of this type, what can we do with it? Now, how do we do this for isfib? Now we want to define the equalities of isfib. Now isfib has got no destructors for its elements, for its objects, but it has destructors for equalities, and there we're going to use this idea. So what's happening? What's happening is that I don't know where to go. Okay, I'm going here. Well, maybe I go here. I'm just playing and go here. So what we have is this situation here, and this really is now a bridge in the universe. It's really the same thing. So I want to have an equality in isfib. To have an equality of isfib, I need it. Yeah. Okay. So to have an equality in isfib, I need first of all a bridge in the universe like this. Then I know that x0 is isfib. At 1, I know that A1 is fibrant, and then I have an equality which says basically that I have a heterogeneous equality, a bridge along A2 between F0 and F1. So I have this bridge, and now in this situation, I'm giving exactly these eliminators. I mean these destructors, namely QE and Koch, but not unique. So I'm giving QE and Koch. So I say if I have an equality between two fibrant types, I get my transports, but I'm omitting the uniqueness. But instead, I co-inductively say, I say that now for any A0 and A0 and any A1 and A1, that the equality, that the bridge type itself is fibrant. So what I'm saying here is that if you have an equality between two fibrant types, you get the transports in both directions, and you also get the proof that the bridge type itself is fibrant. So using co-inductively, we define that fibrant type has fibrant bridges all the way up, and now we can actually prove that this construction is equivalent to having uniqueness. Yeah. Yeah, it's not that good. I think it's fit of the, yeah. It's fit. I mean, yeah, it's fit. Thank you. Okay.
Yeah.
Oh, yes. Good to know. Okay. So to summarize, using this idea of a higher co-inductive type, we can define this fibrant universe, the universe of fibrant types, which is really what we want. That's really what we're interested in. So in a way, this parametricity calculus is just a step to what we want to do. And what we now have to do is to show that fibrant types are closed under type formers. And here, exactly this idea that the equality of some type is an instance of the same kind of type. So equality of pi types is function, I mean, it's not function, I mean, it's a symmetric version of function extensionality, which is another pi type. So this fits very well with this co-inductive definition, because you co-inductively prove that pi types are fibrant all the way up, right? And to do this for W types and M types, you need to have a good choice, an indexed version of W types and M types, and then you can prove that they're fibrant again co-inductive. So the tricky bit is that the universe itself is fibrant, and yeah, so that's some ideas, but we okay. So yeah, it's a summary, and that's all I wanted to say.
You're giving these principles and simple principles of the legal mind.
Yeah.
A fundamental one, I think you didn't address the pretty fundamental, which is much of those principles that any type only ever internalizes prior to the structure. So in the same way that exponentiation internalizes entailment math, then what is it that you want? I have to use some word, I'll say quality. I don't know, what do you want it to internalize? And one formulation of that is your judgmentally quality has zero to do with definitional all that.
Yeah.
The question is, how do you define equality in such a way that the equality type internalizes that judgment?
Yeah, I guess I'm not.
That's how you get.
Okay. Oh, yeah.
Maybe he has a proposal.
No, sorry. You want to say more? No, I'm sorry. I thought you were finished. I didn't want to know.
No, I mean.
Okay. Yeah, I think that to me, this sounds a bit of like a very formalist view. I mean, to talk about judgments, I mean, judgments to me.
So I will reject that.
I know. So I didn't want to be offensive, but
No,
yeah, but but what you say is, really you need to explain things in a formal way. Where I would say the theory I'm creating is reflecting my intuitive, my pre-mathematical ideas. So, and I wouldn't necessarily adopt this principle, but I would say it has to reflect my understanding. I try to explain my understanding of equality in a non-formal way. I'm saying that mathematical objects are given by what I can do with them. Yeah, they're not. I have to define them somehow, but the definition is not the essence. This is the extended view. If I have two, as I say, if I have two functions, then all what I can see about them is what happens when I apply them. And that is for me the attempt to explain equality. And now I'm going to design a system, or we are designing a system. Obviously, we're not starting from scratch, we have lots of history. And the criteria is that this system should reflect our intuition. To me, intuition comes first, and then the system should reflect the intuition.
but besides what Martin principle doing, you first of all have an idea of what equality is,
Yeah.
and then you internalize that notion. Right? But
Yes.
another question. How do you find it? Right?
I mean, I just
But the
to explain it. No?
you can take a sort of Hilbert style approach in which you internalize everything using, implications and so on. So you'll say quality there, speed, EQ layer, I'm just saying, let me just stop.
Yeah.
The point is,
I mean, I'm happy to continue this maybe.
the way in which we got full-throated canonicity for cubical type theory was using this exact.
Yeah.
And in competing cubical type theory, you not get that.
Okay.
And you want canonicity.
I want canonicity, but
We've proven candidates.
No, I'm not, I'm saying, we agree that we want canonicity. I simply said, in the case of the cubical type theory, where God was insisting, and the other approach did not choose.
yeah, but that doesn't mean that you have to insist on this point to get canonicity.
No, I'm not saying there's only one road to Rome. I'm
Yeah.
simply saying that it's coherent with the requirement.
Sure, no, that's
doesn't
good.
have how to speak,
Mhm.
and it hasn't otherwise.
Okay.
The other thing I'll mention is Todd Wilson, I wrote in years ago, telling that the definition of proof.
Oh, yeah. Yeah, it's similar. I think I know what you mean, but slightly different.
Because the idea there is that they capture the full,
Yeah.
higher dimensional information equivalent in a straightforward way.
Yeah.
And they went over with a thought. And so I kind of don't really go along.
Mhm.
Because it seemed like a good idea because it gives you a universal characterization of equivalence in the same.
I think that's maybe this slide is also the co-inductive definition, but this one here, I think is in a way different because it's what we call a higher co-inductive type. And for example, this square root is also it's like a primitive higher co-inductive type. You could also define this using square root, but not so nice. But I think here I think the definition you refer to, unless I get it wrong, is just a co-inductive definition of equality, but not a higher co-inductive type. But which is, I mean, it's quite valuable. I'm just thinking different from what we're doing here.
Further comments? I will invoke the principle of reductio ad equalitatem formulated at the IAS,
Mhm.
which states that when we start asking what is x equals y, then the discussion is over.
No, well, I mean, I thought you meant the syntax. Meaning is quite important.
Okay, maybe I won't stop should I stop it and restart it? Probably it's better.
We have identifiable.
Not stop the share though, stop the recording.
So we do want to stop the share because we have to switch the,
Right, you don't.
yeah.
Stop the share as well? Okay.
Yeah.
Okay, Tart,
Right.
What
Okay,
is-
and then here I stop the recording as well.
Sorry?
what did Chat GPT do for this?
Oh, wait, the recording is from my computer. I have to stop it.
Oh, yeah, okay.
Yeah.
But the hope is this.
Polished up.